What's up, stats? Stirrup here. Hey, I probably told you the wrong page on Wednesday. So I'm actually going to be on page 36 of the books, page 36 and 37. We're going to go over 6-7 as a lecture, but I think you should be fine with this. I hope you're doing well, and I look forward to seeing you on Friday. So 6-7 is calculating the p-value of a one-tailed test. Okay, remember one-tailed means you're greater than or less than. You're not going both ways. Um, so a p-value is the probability of obtaining a result at least as unlikely as the one we obtained by random chance. Okay, so we start with the null hypothesis. So remember our null hypothesis is this, and then we create a alternative hypothesis, and we're going to go down. So a p-value is basically the shaded region. So you could have a shaded region down here. That's a p-value. And we're keeping this as one tail, so it's either direction. So that's what's taking place between those. Um, Shaded region on normal distribution. You have to make sure that you're dealing with a normal curve. Okay. And we can use Desmos in order to get an awful lot of this. So I'm going to be bouncing back with Desmos as well. So let's run through the first example. They say, assume the average price for a movie ticket was known to be $11 in 2010. And has the average price of a ticket risen since then? Assume our plan is to survey 600 random movie theaters, um, maybe throughout the United States. So our null is, and we're just going to use that Greek letter mu, is equal to $11. And our alternative, or again, we're going to use mu again, and then it's greater than $11. Now, we all know we've been to the movies, and it is expensive these days. So let's make this based on our 600 moviegoers. How are we going to go about doing this? Okay, well, we have to figure out our standard error first. And so our standard error in this case, we're going to take, do I have the null state, draw the null hypothesis sampling distribution below, use the normal CDF to complete the uh, p-value. Um, let's see. I don't have, so standard error is the standard deviation. So let's say, I'm going to make up on this one. We're going to say, well, let's make the standard deviation, let's make it $1.50. Okay, I don't see it anywhere in there, so we might have forgotten to put it, but let's just make one up arbitrarily, and let's say $1.50. So my standard error is going to be the standard deviation over our sample size of square root of 600. Okay, um, so I'm going to go $1.50 over the square root of 600. And I'm going to bounce to Desmos because I don't have a calculator with me because I'm down in an office that is not, I don't have my stuff with me. So Desmos, graphic calculator, and I just want to run back to make sure we said $1.50 over square root of 600. Okay, 1.50 divided by square root of 600. So this is going to be 0.06. That's our standard error in our case, so 0.06. Okay, so this is going to come out to 0.06. And I think I did that right. Let me just go back and double check. $1.50 our standard deviation over square root of 600. Yeah, we're good. So if we draw our normal curve out of this, we're going to say, okay, 11 is here, and then 0.06, $11.06, $11.12, $11.18. If I went the other way, I'm going to get $10.50. Subtract 6 from it, Chris. 94, $10.88, and $10.82. So that would be what our normal sample might look like. So use the normal CDF to calculate the p-value. Okay, let's assume this said alpha of 0.05. What would our research decision be? In decision, can we calculate the information? So I'm missing something. And after it says draw a null hypothesized sampling distribution, I don't have anything below that other than using normal CDF to find the p-value. Okay, so if we're going to find our p-value, we kind of have to know, we have to pick a value that's bigger. So what would be an obscurely high number that we could do a p-value on? So I'm going to do it a couple ways, and we're just going to play around with this, see if we can find something here. So let's do our normal distribution, and we're doing 11. That's our mean, and we said our standard error is 0.06. 0.06. Oops, 0.06. And if I hit the plus, it's going to give us a normal distribution. So let's just play around with this. We don't necessarily have values here. So let's take a look. You know, if we were to say we found a ticket that was $11.10, so we had like a 4.7% chance, 4.8% chance in that in our reality. If I came across and I said, oh, I have a ticket that costs $10.55, you know, you're talking about all the area on the curve. So let's bring that up. So let's go to 80 cents, $10.80. That's still an incredible amount. Let's go to 95 cents. So we had a ticket that was $10.95. So basically we're looking at, we're looking at greater than. So if we came across saying we want bigger than 11, well, this is not bigger than 11. So this is obviously a horrible p-value that we deal with. So let's say we choose our alpha of 0.05. What our research decision be? Okay, so 0.05 means I'm looking for 95% of the area. Okay, so I'm going to click this off, and then I'm going to go, I need to find out under functions. It's going to come down here, and we're going to look for inverse CDF. So if we set it at 0.05, that means I'm going to the other direction. So in this case, if we use the 95%, because our alpha is 0.05, so I'm going to do the complement of that 100 minus 5, or 1 minus 0.05 comes to 0.95. So this is showing that basically 95% of our movie tickets would be below $11.10. So that's kind of a, if they're just saying, hey, we want to show this is above $11, that's great, but we chose a pretty low standard deviation that wasn't given to us in the problem, so we just had to make one up off the top. So, that might be one way of looking at this problem. Okay, so on page 37, we're talking about, says caution number 1, make sure that the statistic is in the same direction as the alternate hypothesis describes. For example, our alternative of the movie ticket problem was greater than $11. For this, the theory in which we are trying to find strong evidence above $11, what if our sample produced $10.65? Excuse me. We can't use a simple statistic of $10.65 as evidence that movie prices have gone above $11. So in this case, sample contradicts our alternative hypothesis, and we automatically fail to reject the null, meaning we're not finding evidence to go against our null. Caution number 2, it's bad to use a normal distribution to model data that is not normally distributed. So you use the central limit theorem as a guide to check for normality. Remember, the normality, if you were dealing with just means or average, this has to be, n has to be greater than or equal to 30. If it was less than 30, that's where you use the t sample, but we're not going to deal with that. If we had proportions, we're going to use the equation is n times p greater than 10, and is n times the quantity 1 minus p greater than 10. And this is where we're given some sort of percent that we're dealing with our problem. Okay, and those again go along with our standard error. So standard error, when we're dealing with means, that's the standard deviation. And then if we were dealing with a probability or a percent chance of something happening, this is what we would use for the standard error. Okay, so now I'm going to go to page 105, and you're welcome to try 105 on your own, or you can just kind of follow along and fill it out as you see fit. Let's take a look at page 105. All right, so page 105 says draw a null hypothesized sampling distribution for each, label the 7 positions, draw the statistic and shade the appropriate region that models the p-value, then calculate the p-value, show the calculator command. Excuse me. Problem number 1 says we theorize that coins actually generate heads more than 50% of the time when flipped. We choose to flip a coin 1,000 times and record the results, and we obtain that 50.4% are heads of those 1,000 tossed. All right, so basically our null hypothesis would be mu is equal to 0.5, which is 50%, and our alternative would be mu is greater than 0.5, or we can make those 50, meaning 50%. If we wanted to go ahead and find our standard error in this case, we are going to go 0.5, because that's 1/2. 1 minus 0.5 is also 0.5 over the square root of 1,000. And if we do this math, we're going to come out to 0.016. So that's our standard error. If we draw our normal distribution on this, I know that 0.50 is right here, and then as I go to the right, I'm adding 0.16 or 0.016 to it, so 0.516, 0.532, 0.548. Oops, I didn't mean to do that. 0.548. And then if I went to the left, I'd subtract 0.16 from 0.5, so I get 0.484. If I keep going, I get 0.468, and then one more to the left is 0.452. All right. So now we want to figure out how we're going to do this. Okay. Let's do our Desmos. So we have normal distribution, and our mean is 0.50. Okay, and our standard error we just found, I have to go back and look back at it, is 0.016, 0.016, close parentheses, hit the plus sign on Desmos, it's going to give you your normal distribution. And we want to know, was our result that we got the 50.4%? Well, everything's a decimal. Okay, so I'm going to go 0.504 is greater. So it looks like 40% of our rolls, our p-value is 0.401. So that's the area to the right. So did we find an unfair coin? I think we might adventure into that later. Let's go to problem number 2. Problem number 2 says, it is known that the gas mileage of the Ford Fusion is 32.8 miles per gallon, 32.8 miles per gallon. Okay, on the highway, we theorize that higher octane gas will increase the mileage. We collect 30 random Ford Fusions and run each on a tank of gas. We discover the gas mileage on these cars is 33.9. So we did a study of 30 randomly selected Ford Fusions, and we found that these cars had 33.9 miles per gallon. Okay, so let's go ahead and do our information. So we know that, let's find our standard error. So our standard error, we got, where did we get that number from? Oh, it didn't look like I gave you a standard deviation. So let's say the standard deviation that we give in this case is 4, okay? Then I can go ahead and find my standard error. So I'm going to go 4 over the square root of 30, and that's going to give me 0.73. Oh, they did give you the standard deviation for. I was looking at an old sheet of it. I'm sorry. Let's go ahead and work that out. So if we got our standard error of 0.73, so now we can go to Desmos and see what Desmos is going to tell us. So we can get rid of that, and let's change this. So our claim is that the Ford Fusion is going to get 32.8 miles per gallon. We have a standard error of 0.73. Close the parentheses, hit the plus button. That's our normal distribution on our car. And then we want to know, hey, is it possible that we found a car, or they were incorrect on our thing? So we're going to go, what's the probability that we're going higher? So 33.9. So now we have a p-score here of roughly 0.066. So remember, the p-value, if it was less than 0.05, that meant something. So this is getting closer, and we're just finding the p-value at this point. That's your answer there. All right, let's go to number 3. It says a professional athlete takes on average 220 days to recover from an ACL tear. Medical researchers are attempting a new treatment that will reduce the recovery time. Sample of 64 athletes is obtained for the study, and recovery amount is 206 days. And we also have a standard deviation. So we have a mean. We have a mean of 220. We have a standard deviation that's given to us of 40. And we have a sample of 64 athletes that we're plugging into this event. Okay. And they are saying that their study found that 206 days is the healing time, not 220. So were they onto something? I don't know. Well, let's find our standard error. Standard error is going to be the standard deviation divided by the square root of the 64. So this is going to be, square root of 64 is 8, right? So 40 divided by 8, I think is 5. So we can go ahead and draw our normal distribution, which looks something like this. So we have the 220 right here. We're going to add 5, so that's 225, 230, 230, 235, 235, 215, 210, and then 205. Oh, look at this. So that 206 days is falling down here. So that might be something pretty cool to see. All right, so let's take a look at our, using Desmos, we are going to say that we know that we have 220 days is our normal. We had a standard deviation of 5 days. Our standard error is 5, excuse me. And then go ahead and get rid of this and hit the plus button. So that's our normal distribution for this. So this company is claiming that they have a group that is only taking 206 days. So I'm going to make this negative infinity. And then I'm going to have my max be 206. Ooh, look at that p-value. P-value of 0.003 roughly, or 0.0026. That's less than 0.05. So in this case, we find strong evidence against our null hypothesis. So this company might have found a good treatment plan for athletes. Okay, I know it doesn't ask us to conclude. All right, I'm on page 106, the backside of this page, and we're going to go to number 4. Because currently it is known, let's see, currently it is known that 16.8% of adults smoke. Is the percentage lower in Colorado? We randomly surveyed 500 adults in Colorado. Assume the results of the study show that 17.1% smoke. Okay. So our hypothesis is going to be P equals 0.168, and our alternative is less people in Colorado happen to smoke. Okay. And this is going to now be, if we go down to number 5, is this a one tail or a two tail? It's a one tail, and basically it's a one tail right there. Okay, we were looking then, we feel that Colorado has less smokers, so it's less than. Number 6 then talks about, let's assume the researchers are concerned more about a type 2 error. Should they use a higher level or a lower level of alpha? Okay, so number 6, they should use a higher level of alpha. A higher level of alpha raises the chance of a type 1 error, but lowers the chance of a type 2. So a higher alpha would raise a type 1 error. At the same time, it would then lower a type 2 error from taking place. Okay, so kind of remember that information. Without calculating the p-value, researchers already know they failed to reject the null hypothesis. How did they know that? Well, this is how they know it. They found in their study, for problem number 7, they found in their study 17.1% of the people in Colorado smoke. Well, this is already way below this, and it's below this. So we were above what our hypothesis was. So we automatically just have to say that we have to fail to reject the null. They weren't right. We didn't have less. We actually had more. But we could have done another test to see how much more if this was significant. Okay, down at the bottom, it says currently approximately 62 movie theater goers buy concessions, soda, candy, popcorn, etc. The theater owner wants to increase this percentage with more employees. They assume that a random sample of 100 customers shows 67% purchase concessions. Researchers chose an alpha of 0.08 for this study. Okay, so let's take a look at what they're doing here. Okay, so this is for problem number 8. They felt, if we want to draw this out, they felt that 62%, so 0.62, buy movie tickets. And now they said, hey, we're going to figure out our standard error in order to figure out the rest of this. And this is as percents. So that's going to be 0.62, and then 1 minus 0.62, which is 0.38. And they're going to divide by the 100 people. So we have a standard error in this case of 0.0485. Okay, so let's just round that to, let's make our standard error, we'll round it to 0.05. So then if I continue to shade this, this is going to give me 0.67, 0.72, 0.77. If I go down this way, this gives me 0.57, just subtracting 0.05, 0.52, and 0.47. Those take place there. And then calculate the p-value. So then we want to find out what our p-value is. And they said that originally it was this. The customers that they surveyed were here. Okay, and so we want to show the area to the right of that. So we can jump on to our Desmos, do our normal distribution. So originally we thought 0.62. We have a standard error of 0.05. And then we want to see if people are paying more now, because these guys said, hey, we got a 0.67 situation. Oh, I didn't show the graph. There it goes. So now we have a p-value of 0.158. Okay, so that's, you know, I don't know. Was it good? Well, it's not less than 0.05, so there is evidence that does suggest this, but who knows? But that's our p-value is 0.16 roughly. And then what is the researcher's decision? Well, since for number 10, since p is greater than 0.05, we failed to reject the null. So that means evidence is showing that the null is correct. We do not find strong evidence that more than 62% moviegoers buy concessions because of this prescription. My friends, I hope you are well. I hope this went okay for you. I'll see you on Friday. I hope you all have a great day. Take care of one another. Bye-bye. Bye.